It's visible.
Visible?
Yeah.
Okay. Let me take out the PPT.
Yeah.
When is your exam? This week?
On Friday.
Friday you're having your
No,
exam.
no. It's Monday. The coming Monday.
Coming Monday. Now you told me now that this you are having on exam.
Yeah. Yeah.
Okay, okay. Okay. Quaso process we have done. Inter-event time we have done. This too we have done. Who's doing with you? Kolmogorov we were doing last year.
Yeah. We finished even the graphical presentation.
Graphical presentation.
Yeah.
Okay. Let me see. Yeah, graphical presentation.
Mm.
How to interpret that after that sum. And then we will do after that.
Okay.
Okay. I told you I will be continuing with that.
Yeah.
Okay. Let me take it out.
Mm.
So if the sum is coming, we have to find out like the steps we did with, and finally we have to interpret and the graphical analysis. It's a long one. So the question will be given like the data and 3 as the state it will be, and then you have to solve like that.
Okay.
Graphical analysis. Integrating part I have shown you, and then the constant is coming that I have told you.
Yes.
And then computing the P00, and then finally the graphical representation that I have told you.
Yeah.
The function starting at. Okay. Understanding this I have conveyed. So from that, if you did, what you understand is that the process is time dependent, and the probability of transitioning grows over time, and that it follows an exponential pattern. Okay. And it stabilizes. Okay. So here it's like if the return rate were lower,
Mm.
suppose the return rate were mu 0 1 0. Okay, it was lower. So what would we would have seen? We would have seen higher transition probability. Okay. And if the transition rate were higher, we would move to state 1 faster. This is what we did.
Return rate and transition rate are the same.
Yeah, transition rate. That is, here I'm telling you, no, if the return rate is different, transition rate, like if the return rate is lower, then we would say higher transition probability transition. And then it's transition rate with the probability.
All right.
Okay. This is the interpretation you are doing.
Yeah.
Like the transition matrix you have done. So it is a return rate with the higher transition probability. And if the transition rate were higher, then we would move to, it is according to the transition. The meaning is same. that you have to move from one state to other. Today we will do more that from one state. You remember that we were doing a series of data on the last state, the Markov chain process, one
Yeah.
step, then you're following that way. So that is basically the point is that.
Okay.
So here you will be having the state space, how it will be having. The state space will be there, which will consist on a finite number of state, and for each state I, Kolmogorov forward equation will provide you with a differential equation. And then which will be having transition probability associated with that. So this will result into like the system of linear differential equations. Differential equations. So that is what, so which can be written as d dt of pijt is equals to summation of k represents as pik t u kj. So here pijt represents what? It represents the probability of moving from state I to state j by time t, and the sum will account for the all the possible immediate states k. So now there is a uniqueness of this solution, as you have done that there are three types. So here also you will get some uniqueness of the solution. What is that? So here, given the transition rate matrix, that is Uij, the Kolmogorov forward differential equation will have a unique solution. Means if we know the transition rate, like Uij, I to state j, then
Mm.
we can uniquely determine how probabilities evolve over time. And there is no ambiguity in predicting the system's behavior at any time. Now Markov model using this transition rate, Markov models using transition rate. So here now, since the transition rates, that is Uij, it fully determines the probability evolution. So Markov models are typically described by state space and transition rate matrix. Transition rate matrix is what? The generator matrix.
Yeah.
We did last day, the sum was
Yes.
there. Yeah. So the generator matrix is being represented like A is equals to U denoting Ij. Here Uij means for I not equals to J, it is the transition rate from state I to state J. Okay. And
Okay.
UII means which are the diagonal elements. So UII, which are the diagonal elements, they are negative and they satisfy UII is equals to minus of summation j not equals to I. Uij means the total probability sums to 1. Okay.
Yeah.
Now, why this matters in practical? Because once you know the transition rate matrix A is specified, the entire future behavior of the Markov jump process is uniquely determined. Like you have done linear algebra.
Yes.
There you have system of linear equation and you get either a unique solution or no solution or infinite number of solution.
Yeah.
Kind of that. Okay.
All right.
Yeah. So here you have understood if you go for the matrix form of the backward equation, like we did with the matrix form, but if I want to do for the backward equation, then how I will do this? So it is on slide number Kolmogorov backward. So here it will be what it describes, the backward differential equation, Kolmogorov's backward differential equation describes the evolution of transitional probability in Markov jump process, but it take a different perspective compared to forward equation. So here in the time homogeneous case, the time homogeneous case, the backward equation will be written as ddt of pt, that is apt. Okay, so now what is my pt? pt is the transitional probability matrix. Okay, so here PIJT, what it represents? It represents the probability of transitioning from state I to state J over time T. Okay. Now A is called the generator matrix with entries Uij. But you have to remember that unlike the forward equation, which what it describes? It describes evolution of probabilities from the evolution. No, from it is the evolution of probability from the initial state forward in time, and what the backward equation does? Backward equation describes how the transition probability evolves by looking at past states. Okay. So if I tell what is the difference between forward and backward equations. So first, what is the perspective here for both the things? So here you are having forward equation and you are having backward equation. So it follows probability evolution from past to future. And backward equation looks from present to past. Obviously backward.
Yeah.
So it is going backward. And what is the application? So if I talk about the application, so it is used when initial distribution is known and we want to predict future probability. And here it is used when we are interested in conditional probability, focusing on initial states. Okay. And it is based for easier for solving initial value problems, and it is more useful in backward induction problems. So easier for backward induction problems. And it is for initial value problems. And what you do basically, common users for this, here we predict how a system evolves over time. And here it evaluates expected rewards and optimal decisions in control problems. Okay. And the solving, how we solve this Kolmogorov backward equation. So the general solution of backward equation in an it follows an exponential matrix. So it is PT is equals to e to the power at. So e to the power at is what? It is the matrix exponential, and which we can compute as e to the power at is equals to summation n equals to 0 sigma at to the power n by n factorial. Okay, this is useful for computing transition probability where the initial condition is given at the final time rather than the start.
Okay.
So where this Kolmogorov are used, like stochastic control problem. If I say about the application is in stochastic control problems. Okay, so like optimal decision making, you can say, or reinforcement learning, like future option, all those cases we use it.
Yeah.
Yeah. So now Kolmogorov backward differential equation for the HST model. Next, you are having for the time homogeneous HST model, Kolmogorov backward differential equation you can obtain. How? Using the general backward equation. So let's see. Kolmogorov's backward for the HST model. So that is what? The HST model is what? The HST model, it refers to a Markov Jump process where a system transitions between three states. What are the states? Say healthy, say sick, and diseased. Okay. So now, if we apply Kolmogorov backward differential equation to find out that how the question being, if I consider this case and I have to find out how the probability of remaining in the healthy state changes over time. So here first we'll use the template which we use, that is, so the answer, how to deal with this type of question. The backward differential equation follows the general form. That is TdT of PHHT is equals to mu of HH PHHT plus mu HS PSHT plus mu HD PDHT. Okay. So here, what are the notations? Where PHH, it represents the probability that a system starting in state H remains in state H after time t. What is PSHT? It is the probability of transitioning from sick, that is S, to healthy, H, over time. And next, PDHT, that is probability of transitioning from diseased to healthy, H, over time T. Okay. But in most practical cases, D is an absorbing state. Absorbing state means P of DHT 0. Okay. Now we substitute the transition rate. So next we will substitute the transition rate. So that is using transition rates for the HST model. How we will rewrite? DDT P of HHT is minus of this plus mu PHHT plus PSHT. Okay. So here, this is my transition rate. So this is the transition rate from H to S. That is healthy to sick. Okay.
Yeah.
Now mu is what? Mu is the transition rate from H to D. So that is healthy to
This is
diseased. And minus this for mu, that is PHHT. It accounts for what? Probability loss due to transition from H to other states. So S or D. And this SHT. That means probability of transitioning back to H from S. Okay. So here, what is the interpretation of this? So here, the equation which we have written, it describes how the probability of staying in A changes over time. Okay. And if no transition back, from sick, that is S, to healthy, that is H, is allowed, then P of SHT is equals to 0. So then the equation simplifies to d dt of PHHT is equals to minus sigma plus mu P of HHT. Okay.
Yeah.
So this represents an exponential decay.
All right.
And if recovery from S to H is allowed, so the term P of SHT introduces a feedback mechanism affecting how long a system stays in H. So this is the way we can do this.
All right.
So there are certain special cases you can say. So here the equation which you have written, this one, what does different mean differently? So here it is minus the transition rate plus mu. So here this term, it represents
Yeah.
the rate at which individual leaves state H. It can be either by becoming sick or dying. So it can be two cases. By becoming sick, that is S at rate lambda, or dying, that is rate at rate mu. Okay. And here there is a negative sign. What is the negative sign telling? The negative sign states or indicates a loss of probability mass from the H state. This is this one. Now we have a different part also, that is minus this again PSH.
Yeah.
So that is what? PSHT. That term, that is SHT, this term represents the probability of returning to H after first transitioning to S. Okay. So
Yeah.
now, if suppose no recovery is possible from S, so then PSHT is 0 and this term will disappear. So there can be some special cases also in this case.
Mm.
Special cases. What are they? Suppose case 1, no recovery from sick. No recovery from sick. Yes. So that is, if an individual, suppose who becomes sick, never recovers, that means P of SHT is 0. So the equation is simplified to d of dt PHHT is minus plus mu P of HHT. Okay. So this is first order linear differential equation. And we can solve it again using exponential decay. So that is PHHT is equals to PHH0 e to the power minus theta plus mu t. Okay. So this means the probability of staying healthy decreases exponentially over time. The probability of staying healthy decreases exponentially over time. This is one. Second, the rate of decrease, it depends on combined transition rate, correct?
Yeah.
And the larger the values of theta and mu, the faster an individual leaves the age state. Okay. Now, second, case 2. That is recovery from sick. That is S. Is possible, might be. So,
Yeah.
if an individual recovered, so from S to H, so PSHT is not equals to 0. Means the system allows for the possibility of cycling between states. So then the equation will look like ddt P of HHT is minus theta plus mu P of HHT plus theta PSHT. So that means it depends on how it depends on how PSHT evolves. Okay. So here in this case, we must jointly solve the equation. So for this, we will jointly solve the equations. That is for PHHT and PSHT, which will lead to system of differential equation.
Mm.
Now, solving for differential equation. So here, to solve for this, suppose to solve TDT PHHT is plus mu PHHT plus PSHT. Okay. Now we will consider different approach. Why? Depending on whether P of SHT is known. Correct? So here the case 1 will be exponential decay solution. So that is if PSHT is 0, that means no recovery. Then we will solve for DTT PHHT. So that is minus this, that is PHHT. So if I separate the variables and integrate, so this of D of PHHT by P of HHT, that is minus this plus mu integrating dt. Okay. So then that is ln of PHHT, that is theta plus mu t plus c. So that is P of HHT is e to the power minus plus mu t. This is case 1. Now recovery from S was there.
Yeah.
So case 2 is recovery from S. Sick. So if recovery is possible, the system will require solving multiple differential equations.
Isn't that the one we did before?
Yeah, but the equations we haven't done. Na?
Okay.
This we in the previous thing I told you that these are the cases we can do, and these are the ways I am telling you about.
Okay.
Like how in this way you separate and integrate.
Okay.
Okay.
Yeah, sure.
Straight, showing you. This one. I told you that there are two cases, this and this. Now we are doing it. How to do that? Means in mathematical, if it come, then you can do na.
Okay.
Okay.
Yeah.
Yeah. So here it is the first one. If this is the equation, then if it is a first case and you are doing the exponential decay solution, differentiating and then separating the variable and you are integrating. And for the second one, it is recovery from sick. Here you will use multiple differential equations simultaneously. And what you will incorporate? The evolution of PSHT. Okay.
Yeah.
So now the next it is having the right hand side. So that I have already told you that what the first term states. So if I write the equation following the next slide, we have derived the backward differential equation for PHHT. So ddt of PHHT is what? Minus of theta plus mu PHHT plus theta PSHT. Okay.
Yeah.
So if I break down the first term, it's staying in state H, means this one. So here, the explanation is at time t equal to 0, the system will start in healthy. Now, this is a force of transition which will put the system out of S. So that means the force is represented by this. So here, the thing is determined rate at which a person moves. Here it will be from healthy to sick. And what is mu? Mu is the rate at which the person moves from healthy to deceased. And the probability of staying in H over an interval of time is PHHT. That is the probability. Staying in healthy. So if you multiply this together, that is minus theta plus mu PHHT. This together, it represents the probability flow away from H.
Okay.
Okay. And the second term explanation. So the second term is what? PSHT. That means the system can first transition from healthy to sick at rate this. And once in sick, the system may return to healthy over an interval of time t. And the probability of going from sick to healthy over time t is PSH. Okay. And if we multiply together, so first transition from H to S and later then from S to H.
Okay.
So now we can thought it as of like balancing two opposing force. Like first it is healthy to S, then S to H. So ddt PHHT is equal to minus theta plus mu PHHT plus theta PSHT. Okay. So here we can thought it as balancing two opposing force. Okay.
Yeah.
So first it is loss of probability from state H, that is due to individual leaving H. So why? It will be either by getting sick or time captured by minus theta plus mu, PHHT. Okay. And
Yeah.
then second, we are having gain of probability from state S back to H. Okay. So
Yeah.
here, some individuals will recover from S and will return to H, which is known as theta PSHT. What does this equation tells? This equation tells if there is no recovery from S, so then PSHT will be 0. And the probability of staying in H exponentially decay. And if recovery is possible, then it depends on the recovery behavior.
Okay, so then it becomes an absorbing state.
Exactly. Exactly. Now we are having Kolmogorov's forward equation. So till this much clear. Kolmogorov backward equation we did, and this one.
Yeah.
So now Kolmogorov's forward equation. Similarly, we will do for the forward equation. So that is the forward equation. As I told you, it describes based on probability of transitioning from other state into sick over time. So what is the general equation here? ddt of PHST, that is summation of K represents S, PHK T mu Ks. Okay. So here we will identify the relevant transition. That is, the system can stay in H and then it will transition to S. Why this occurs? This occurs at a rate of, and it depends on the probability of staying in H. So that is PHHT, the probability. Okay, so that's why the Kolmogorov forward equation for PHST, Kolmogorov forward equation will be ddt of PHST is theta of PHHT minus theta plus mu PHST. Okay, so here probability gain from state H to S. This one it interprets H to S, and the full thing which I told you, probability loss due to individual transitioning from S to other state. And backward I have already discussed with you.
Yeah.
So forward, it focuses on forward, it focuses on how probability flows into S over time. Okay. And what is backward? Backward is it focuses on how probability flows out of S over time. Next, forward, holding times and occupancy probabilities. Holding times and occupancy probabilities. So what are this? In Markov process, the amount of time spent in a particular state before transitioning to another state is known as holding time.
Time.
Yeah. And this is fundamental concept in continuous time Markov chain and plays a crucial role. The amount of time spent in a particular state before transitioning 、 to another state.
、
Another state. is known as holding time. So memoryless property we have done.
Yeah.
It is not depending on the current one. It is depending on the current one, not the previous one. So first, memoryless property of holding time.
It's kind of like the Markov chain property.
Exactly. It is so part that na, the Markov jump process though. So it will be like that only. The holding time in a state follows an exponential distribution. And this property, that's why ensure that Markov process remain in the memoryless property. Okay. So
Yes.
meaning that the probability of staying in a state for an additional time, given that it has already been there for t, it does not depend on t. Okay. So the equation goes like P of t greater than t plus u, given t greater than t is p of t greater than u. Okay. So here t represents what? T represents the holding time in a given state. Represents holding time in a given state first. And what is this equation representing? T greater than t. It states a probability that the system remains in the state for an additional time, given that it has already remained for time t. And this is identical to this one, left hand side, right hand side, meaning the past duration does not affect future probability.
Mm.
The past duration does not affect future probability. So the time until the next transition does not depend on how long the system has been in the current state. Holding time in a time homogeneous Markov process must follow an exponential distribution to satisfy this property. The exponential nature, it ensures that the probability of transitioning only depends on the rate and not on when the system entered the state. Your main thing is the rate.
Right. Okay.
Next, exponentially distributed holding times in Markov process. Okay. So for a continuous time Markov process, the probability that the system stays in a given state for at least time is given by P of t greater than et exponential. Okay. So here mu is what? Mu is the transition rate. Okay. So that is the rate at which the system leaves the current state. So here also, suppose this transition rate is large. So if mu is large, then the system transitions quickly to another state. Okay. And if suppose mu is small, then the system linger in the current state. So suppose, let's do a question. Suppose a system in state S has a transition rate 0.2 per minute. This is the question. So the probability of remaining in state S for more than 5 minutes will be what? That is, so the answer will look like P of t greater than 5. That is e to the power minus 0.25. That is e to the power minus 1. So say 0.3679. So that means 36.79 probability percent that the system remains in the same state for at least 5 minutes. Okay. So this is the second one. Now, the third one, that is occupancy probabilities. That means while you are holding time, it tells us how long the system remains in the state. Okay. So occupancy probabilities describe the likelihood of finding the system in a given state at a specific time. So say for Markov jump process, what will be the occupancy probability? PIT. It is the probability that the system is in state I at time t. Okay. So this is governed by the Kolmogorov forward equation. So here the equation will look like P of IT is equal to summation of ij not equals to I. So PJT mu of Ji minus Pi so summation of k not equals to I mu ik. Okay. So here the probability of being in state I at time t depends on what? The probability of transitioning into state I from other states. Okay.
Yes.
And second, the probability of transitioning out of state I to another state. So this probability evolve over time. It describes you how the system occupies different state as it transitions. So basically holding times in Markov process are exponentially distributed and it ensures the three property and the probability of staying in the state for at least t time follows p t greater than t exponentially. And occupancy probabilities determine the likelihood of being in a particular state at time t, which is being governed by the Kolmogorov forward equation. Okay.
Yeah.
Now, next you are having this we have done distribution of holding time and this one. Okay. The data is given and you have to do it. So holding time, occupancy we did. Now holding time, homogeneous Markov jump process. So what is that? In a continuous Markov jump process, the time spent in a particular state before transitioning to another state, it is governed by an exponential distribution. Okay. So the first holding time, it refers to what? It refers the first holding time refers to the duration the system remains in its initial state before making it first transition. Okay. So here, if I consider for exponentially distributed first holding time, exponentially distributed first holding time. So then for a Markov jump process, here if you are having the transition rate which I have already defined, mu ij. So that means the holding time in state I before transitioning is an exponential random variable. So here lambda I will be what? Minus mu I is equals to summation of j not equals to I mu ij. So that means lambda I is the rate at which transition occurs out of state I. Okay. And what is this rate? So mu I is the self transition rate. That is typically negative and it is equal to the sum of transition rate to all other states. And what does that sum account to? So summation of j not equals to I mu jj, it accounts for all possible transactions. Transitions from state I to other states. So the time the system remains in state I before moving to different state is an exponential random variable, which is mean 1 by lambda I. So now you know that if the denominator is large, then the system will transition out of state I quickly. So 1 by lambda I means if your lambda I is large, then the system transition out of state I quickly. Okay. And if it is small, then the system stays longer in state I. Next, we will continue with this. There will be probability of no transition until time t, and then I will do with an example, and then we will go for the probability of remaining in state t. Any problem till this much?
No.
Okay. The screen wasn't shared?
It was.
Okay. No, here it is not showing stop present. Okay. Thank you.
All right. Thank you.
Yeah.